Hey there everyone, this is Jeremy McWhorter and this is my lab for circuits. So to begin, we have to introduce this lab. And first to introduce it, we got to understand the goal of what we're trying to get at here. So in this lab, we are trying to kind of understand how the different setups for circuits, how that changes the different voltage and current measurements across the circuit. And the principles we will be using are the principle of energy conversion, energy conservation across the circuit, and then that is also applied to Kirchhoff's current law, that current is conserved across the circuit. And then up to on the top right, we have just the diagram of one of the setups for the circuit, and just a preview of these results. Theoretically, the current will have a 0 amp difference after completing a full loop based off of the conservation of current, and then the current will follow the path of least resistance, and that comes into play with the different resistors that we have. And then capacitors permit the flow of current until they're fully charged. So there's current flowing until the capacitor is charged up. So the equation that we'll be using is the conservation of energy and Ohm's law. Up here we have just the conservation of energy and in the form of potential difference, and those are just three different ways to kind of display that conservation of energy. And then below we have Ohm's law. Here's the kind of the pyramid of the relation between voltage, current, and resistance. So yeah, there are the three different ways you can interpret this pyramid for Ohm's law. So first, here you go on the right, you can see the photo of the setup of the current. So the predicted current across the wires and circuit is 18 milliamps, but the actual ends up being 17.5 milliamps because we're doing this in the real world instead of a simulation. There's just some sort of resistance within the wires, and then other things such as the batteries and all that. And then when in reverse, it reads negative 17.5 milliamps. That just kind of shows the conservation of current. Then the addition of the voltmeter. So the voltmeter read 2.97 volts and then 0 amps. The voltmeter read 2.97 because of the voltage of the batteries, even though they should theoretically add up to 3 because of just resistance within the wires. So here is just the diagram of the different locations that they wanted us to measure the potential difference across the circuit with the two batteries at point A and point B. And here on the right are the measurements that we found across the circuit. So as you can see, AB is at the max potential for potential difference, which is 2.97 volts, and then you just see how it changes across the circuit. So now we are graphing potential difference. As you can see, it just steadily increases with the battery, and then it stays constant until it comes across the resistors, and then decreases steadily. And then, so the predicted potential. So the predicted is that the sum of the voltages within the circuit equals 0, because there should be no potential difference when completing a loop around the circuit. And this ends up being true, and then this is displayed with just the sum of the voltages within the circuit, and they equal 0. And the current within the ammeter does not change because there's no current flowing through the voltmeter because it's an open circuit. So here are just the calculations between the resistances and the resistors and the resistance that they end up creating. So as you can see, they come out to about 48 and 100 ohms, which is what they truly are. And then you can see that with the wire and the ammeter, because the current is open, they're equal to 0. And then just a footnote here at the bottom is that because the current takes the path of least resistance, it goes around the higher resistor, the higher 100 ohm resistor, and it reads 0.06 instead of 0.02. So next we are asked to set up an RC circuit, so that is with the capacitor. So once the current is connected, the light bulb kind of charges, is lit up originally, but then it slowly dims because the charge is going into the capacitor. And then once you disconnect the batteries, because the capacitor is fully charged up, the light bulb is lit up, and then it slowly diminishes as the charge leaves the capacitor. One thing to note here is that the capacitor lets current flow through until it is fully charged up. So here we're asked to calculate the charge and discharge time with the different light bulbs, and as you can see, we're measuring on the right. Then just here are the times. As you can see, the higher resistance battery discharges over a longer period of time. And then here we're asked to graph the time dependency of between voltage and capacitors. As you can see, they follow these equations right here, the natural log equations. And then right there is the graph for the natural log V over V naught. Okay, what if and why? So we're asked to do this lab in real life, but however we did actually